Assalamualaikum, my name is Nurul Anis binti Yazid.
Assalamualaikum, my name is Nurul Izza binti Sabtu. We were asked to explain two theorems for this video presentations. The first theorem is every cyclic group is abelian, and the second theorem is Cayley theorems. Every group is isomorphic to a group of permutations. For the first theorem, every cyclic group is abelian. To prove this, let G be a cyclic group and let A be a generator of G, so that G equals to generator A equals to A power of n, such that n is any element of integer. If G1 and G2 are any two elements of G, there exists integer R and S such that G1 equals to A power of R and G2 equal A power of S. Then we prove the commutative law. We will get G1 G2 equals to G2 G1. Therefore, G is an abelian. Hence, we can then conclude every cyclic group is abelian. Now we have the example. Show that integer modulo 12 is abelian. First, I need to show that this group integer modulo 12 is cyclic. We know that in element integer modulo 12, the elements are 0, 1, 2, 3 until 11. So, I need to find all of the generator to show that integer modulo 12 is cyclic. So, I will try one by one. For instance, 1. 1 power of 1 is 1, 1 power of 2 is 2, until 1 power of 12 is 0. Then I will try for another element to get all of the generator. So, integer modulo 12 is generated by 1, 5, 7, and 11. Therefore, it can be concluded that integer modulo 12 is cyclic. Then I will prove the abelian. Integer modulo 12 is a cyclic group with 1 as its generator, that like we get before this. So then integer modulo 12 equal to generator 1 equal to 1 power of n, such that n is any element of integer. Then if 5 and 7 are any two elements of integer modulo 12, there exists integer r and s such that 5 equal to 1 power of r and 7 equal to 1 power of s. Then we will prove the commutative law, which from 5 times 7 until we get 7 times 5. Therefore, the answer is integer modulo 12 is abelian. So it is proof that the theorem every cyclic group is abelian is true. Next, Anis will continue the presentation.
Now, I will explain about Cayley's theorem, which is every group is isomorphic to a group of permutations. To prove the theorem, we let G be a group. The left regular representation provides a map of phi that is mapping from G to symmetric group of G defined by phi of x equal to lambda x. To prove the theorem, we must verify that phi is 1 to 1 and phi is a group homomorphism. Phi of G is a subgroup of symmetric group of G by theorem 8.5, and phi that is mapping from G to phi of G is an isomorphism. To prove the theorem, first we have to show that phi is 1 to 1. Suppose that A be in G and phi of A equal to phi of B, then the permutations lambda A and lambda B are the same. So, lambda AE equal to lambda BE, thus AE equal to BE and A equal to B. So, phi is 1 to 1. Second, we have to show that phi is a group homomorphism. Let A be in G, then phi of AB equal to lambda AB and phi A phi B equal to lambda A lambda B. We must show that the two permutations lambda AB and lambda A lambda B are the same. So we let G in G. Lambda AB of G equal to AB G. Thus from the calculation, we get lambda AB equal to lambda A lambda B, which implies that phi of AB equal to phi of A P of B. So P is a one-to-one homomorphism which completes the proof. To make the theorem more clear, I will show one example, which is show that the group of G equal to 1 omega omega squared is isomorphic to a group of permutations. Since the questions already stated that G is a group, then we just need to find the group of permutations. Therefore, we let G prime equal to F1, F2, and F3. Then we find for F1. F1 equal to 1 to 1, omega to omega, and omega squared to omega squared. To get the permutation, we will multiply the first element of G, which is 1, multiply by the second row of F1, and we will get the identity. Next is we find for F2. Just like how we find for F1, we will multiply the second element of G, which is omega, by the second row of F2, and we will get omega, omega squared, and 1 for the second row, and we will get the permutation of F2 equal to 1 to omega, and omega to omega squared. Next is we find for F3. We find for F3 by multiply the third element of G, which is omega squared, by the second row of F3, and we will get omega squared, 1, and omega. And therefore, we will get the permutation of F3 equal to 1 to omega squared and omega squared to the omega. Thus, the group of permutation of G prime consists of identity 1 omega, omega squared, and 1 omega squared and omega. Therefore, we can conclude that the group G is isomorphic to a group of permutation which is G prime. That's all from our group. Thank you.